Welcome to the last portion of Lecture 3. We're on Lecture 3G, looking at complex ion equilibrium. So for complex ion formation, here we have a complex ion forming between a metal cation and a Lewis base. Remember, a Lewis base is something that has a lone pair of electrons that it can donate to a cation, usually a metal. So as an example, we can have silver interacting with ammonia, where that nitrogen has a lone pair of electrons, and we form a complex, a silver ammonia complex. Notice that we do have our brackets here indicating that this is a single species with a positive charge on it. So normally these brackets mean concentrations, but not when we're expressing them in the form of a complex. These types of complexes are very common in biological systems. So if you're going more into a biochemistry field here in our program, you may encounter these quite often now. The Lewis base in these complexes, so the ammonia here, is something that we would call a ligand. And if you go on in inorganic chemistry or a bioinorganic chemistry field, you will use the term ligand quite frequently. So complexes reach equilibria that are very heavily product favored. In other words, the equilibrium is shifted way in that direction. And that's a little bit different than a lot of the equilibria that we've looked at in previous lectures. And it does cause a bit of a problem when we're doing our calculations, but we have a way around it, and we're going to explore that today. So as I mentioned, the equilibria are very heavily favored in the forward direction. And what that does is it gives them really large equilibrium constants. And these equilibrium constants, when you have these metal ligand interactions, are called formation constants, Kf. So again, the big K just tells you it is an equilibrium constant, and it's a very specific type of equilibrium that we're looking at, and that's the formation of a compound or of an ion that forms between a Lewis base, a ligand, and a metal ion. So as an example here, a copper ammonia complex, very commonly looked at for learning. It's very well behaved. You do it a lot in the lab. But we have copper 2 plus 4 ammonia. It gives us a copper ammonia complex. Notice that the ammonia has no charge. The copper has a 2 plus charge. So when the complex forms, it still maintains that 2 plus charge because all we do is add up all the charges. So 2 plus 4 times 0, that gives me 2 plus back. And look at the size of this formation constant. So this is an equilibrium constant at 10 to the minus 13. Most of the equilibrium constants we've looked at up to this point all have a negative in front of that exponent, but here they are very positive. Now, one thing we can generally infer is the larger the Kf, the more stable the complex. However, you do run into the same issue as we did with our KSPs, is the stoichiometry of these complex formations can skew that a little bit. So you do have to be careful when you're looking at the stability. So notice also that if you have a metal ion and you end up with an ion out here, an ion is still going to be in solution. It is not going to be a precipitate. We do not have charged precipitates. And so they are still ions floating around in solution. So it's always important to remember that. It is possible to have negatively charged ligands, and however, we usually have a fairly large number of them, and we can end up with a negatively charged complex as well. But they're still not precipitates, they're not forming solids, they're just forming complex ions. So let's look at an example. So we're going to take 0.2 moles of copper sulfate, and we're going to add that to a 1 liter solution of 1.2 molar ammonia. We want to know what is the concentration of the copper at equilibrium. So in other words, how much copper is not going to be complexed when in that solution. We have the Kf here of 2.1 times 10 to the 13th. Now, because this equilibrium constant is so large, it's very difficult to do with an icebox. And this is because of the way calculators work. They're not good at differentiating super small differences between numbers, except unless one of those numbers is 0. If we have two numbers that aren't 0, then it becomes more of an issue. So we're gonna do a little trick here. We're gonna set up something that's called an icky box. So we're just going to add an additional C. And what this additional C is this guy right here. So we still have our initial conditions in here. And now what we have for this first C, this is where the difference is. We're going to say that this is a 100% reaction. We're going to allow this reaction to move completely in the forward direction as far as it can possibly go. And you have to look at the number of moles you have and compare the stoichiometries. So I can see that my limiting reactant here is going to be the copper 2 plus because I have more than 4 times the copper, or I have more than 4 times ammonia than I have of copper. And so the copper will run out first. So I'm going to have minus 0.2 of the copper. So I'll have no copper left if I go 100%. I'm going to move minus 4 times 0.2 of the ammonia. And again, I have that 4 for the ammonia because of the stoichiometry in the reaction on the previous page. And I'm going to make 0.2 moles of the complex. Okay, now what happens next is the next change. Because I have pushed my reaction completely to the right, I'm going to allow it to reach equilibrium by coming just a little bit back to the left. And if we think about what equilibrium constants are, because I have a very large equilibrium to the right, it means that I have a very small arrow has to come back to the left. So remember, for an equilibrium to exist, I have to have forward reaction and reverse reaction. So my forward reaction is really big and my reverse reaction is really small. So this allows me to get back to having small numbers for my x's rather than trying to subtract two numbers that are very close and might differ in the decimal points outside of what your calculator can handle. So for my change, as this reaction comes back a little bit, I'm going to lose a little bit of my copper ammonia complex. How much? I don't know. I'm going to lose X amount of it, but X is going to be small here. For every one of the coppers I lose, I'm going to get 4 ammonias back. And so I'm going to have plus 4X, and then I'm going to get 1 copper back, so plus X. Now to get my equilibrium concentrations, I still do the same thing as before. I just add everything up. 0.2 minus 0.2, 0. 0 plus X is X. 1.2 minus 4 times 0.2. Now this is going to be 0.8. So 1.2 minus 0.8 is 0.4. 0.4 plus 4x gives me 0.4 plus 4x. For my copper complex, I started with 0. I gained 0.2 in the 100% reaction. I lost x when it went back in the reverse direction. So now I have 0.2 minus x. So now I have all of my concentration in terms of one variable x, and I can plug those into the equilibrium constant expression. My equilibrium constant expression, still products over reactants. I have to use stoichiometries as exponents. So I have my copper ammonia complex 2 plus, that has a coefficient of 1, so it has an exponent of 1, over concentration of copper 2 plus, that has a coefficient of 1, so that exponent is 1, times concentration of ammonia. Now the ammonia has a exponent of 4, so I have to raise my concentration of ammonia to the 4th power. That's going to all be equal to 2.1 times 10 to the 13th. That's my KF. So now I plug in my values. I have 0.2 minus X for my complex, X for my copper, 0.4 plus 4X raised to the 4th power for my ammonia, and that's going to be equal to 2.1 times 10 to the 13th. Now, this is going to become a huge problem. We're going to have, something X to the 4th on the bottom, and it's really going to be a mess. Now, let's see if we can clean it up a little bit with some assumptions. Since that KF is so large, I know that it's going to be pushed far to the reactant side. What that means is that the reverse reaction back to the reactants in that second change line that we had in our icky box is going to be very, very small. So I know that X is going to be very, very small. And I'm going to say that X is much smaller than 0.2, and even 4X is going to be much smaller than 0.4. So I'm going to say that 0.2 minus X is still pretty much 0.2. and 0.4 plus 4x is still pretty much going to be 0.4. We'll take a look at it after we're finished to see if our approximation was reasonable. As you can see, this really simplifies my equation. Now I just have 0.2 over x times 0.4 to the fourth. That is easy to plug into your calculator to solve for x. And when I do that, I get an x value of 3.72 times 10 to the minus 13. We can see that even if we multiplied by 4, it's still significantly less than 0.4, and it's certainly much less than 0.2 as well. So we were validated in ignoring these x's here. It would not have changed the outcome for that value of x. So we can also take a look at how solubility and complexation are related. Now, we know that complexation equilibria lies far to the right, which means that even if you have a very small amount of either metal ion or your complexing agent, you can still form a complex at extremely low concentrations. Let's go back and look at silver in a silver chloride solution. We know also, it was one of the first reactions we saw in this section, was that ammonia will complex with silver plus and remove it from solution. When the ammonia reacts with the silver plus, just like acids did, it turns that silver into a different compound, and here it turns it into a complex. But it removes that silver ion out of the solution as silver ion by itself, and so that removes it out of the equilibrium value for the KSP. And what this does is it tells the KSP equation, the solid, that there's not enough silver in solution anymore, and so it has to keep dissolving more of that silver chloride in order to meet the silver ion concentration. As long as ammonia continues to complex it, it'll continue to dissolve the silver chloride. And so slightly soluble salts can become very soluble if you can find an appropriate complexing agent. Let's take a look to see what that looks like in practice. So here we have just a silver chloride solution in water. It's just a little cloudy, probably just some very small particles of silver chloride floating around. But for the most part, you've got a few silver ions floating around, mostly just water. Up in here, we've got an ammonia solution. We squirt the ammonia into here, and what the ammonia will do is it will grab whatever silver ions are floating around in solution and remove them out of the equilibrium constant expression, because now they're silver ammonia complex ions, they're not silver ions. And so as those get removed, more and more of this silver chloride has to dissolve. And you can see that just by adding a little bit of ammonia in there, if it's concentrated enough, you can actually dissolve all of that silver chloride out of that solution. It's one of the ways that they used to get silver salts out of old photography solutions, is to precipitate it first with silver chloride, because that does a very good job of getting it out of solution. And then you can separate the silver chloride just by pouring it through a filter paper, and then use ammonia to remove it from the silver chloride. And there's an electrochemical process you can use to get your silver back, because it used to be worth a lot of money, and it made some of developing quite expensive. Well, that finishes out Lecture 3 material. It was a lot of stuff this week. If you have any questions on any of the material that we covered this week, please make sure you either put it into the WooClap for the Panda session, or you're always welcome to come see me or send me an email.